what have we learned from our simple examples? That a multiplication table is at the heart of a simple decomposition of probabilities. In other words, there appears to be, in certain settings, a natural rule of products. Let us promptly generalize and abstract this into a definition. We will say, as a matter of definition, that two events A and B in a probability space are independent if the probability of A intersection B is equal to the probability of A times the probability of B. You should bear in mind that in definitions, the definitions are always two ways, right? But we'll usually dispense with the and only if portion of the definition. It is implied. It's part of the definition. Here is now a mathematical definition of independence. We should keep in mind that this, in principle, abstracts out what we commonly understand by independence in ordinary language. But it says more. It says things very precisely, very concretely. Whenever we talk about independence, probabilistic independence, though we'll usually drop the word probabilistic in our setting, independence is always in a mathematical or probabilistic context. When we say independence, we mean precisely the object on your screen. Nothing more, nothing less. Intuition, our feelings for independence in ordinary language can all affect, help, understand the problem. But ultimately, when push comes to shove, that mathematical relation is what we mean and we understand by independence. Of course, this relation did not come out of a vacuum. It arose out of simple combinatorial settings, out of simple multiplication tables of possibilities. And we understand that in various settings, this kind of relation emerges. What we now do in such a definition is take that observation and expand it widely, greatly, vastly, to a general abstract setting, where intuition may be aberrant. We'll see examples shortly. But for the time being, let's go ahead and say we have a very simple definition. We hardwire this into our brain. This is what we mean by independence. Let us explore what its consequences are. To begin, that definition looks vaguely familiar. Why? Well, it talks about the probability of an intersection. Where have I seen that before? And a little thought says, oh well, we've seen that in our definition of conditional probabilities. Here is a chaining rule. We can write the probability of the intersection of two events in terms of a chain involving a conditional probability of one event with respect to the other. Now this is generically true, as long as, of course, the event B has got positive probability and the objects on the right are defined. But now we have another relationship for an intersection probability. But this requires more structure in the events. What if the events A and B are independent? Well, that says the intersection probability is given by a product of probabilities. Now, by examining the right-hand side, we can immediately deduce a relationship for conditional probability. But before we do that, let's pause to observe that our chain rule for conditional probability can be written in the other direction just as well, by conditioning on the event A. And now by examining the objects on the right-hand side, we can simply deduce that if A and B are independent events of positive probability, then the conditional probability of A given B is just the probability of A itself. And the conditional probability of B given A is just the probability of B itself. In other words, we are in a political age, and so we should want a slogan. So here's our slogan. Mathematical independence, probabilistic independence, captures a very intuitive idea that if two events A and B are independent, then the occurrence of one does not affect the chance of the other. this is very promising. This is exactly what we'd hoped that a definition of independence would try to capture. But of course, we now have a formal mathematical structure which captures this. So again, independence means that a joint probability is a product of probabilities. Independence is a rule of products. Before we move on to applications of more heft, we should examine the definition a little bit more and see if certain other attributes emerge. So let's start with a very simple question. I've given you two events A and B. The moment I give you events A and B, other events are implicitly part of the structure. For example, the complements of these events. If I tell you that A and B are independent, well, that means we have a rule of products. Does it say anything about A and B complement? Now, instinctively, I want to say that if A and B are independent, then A and B complement are independent, natural. But of course, this is instinct, based upon our experiences. The question is, does our formal mathematical definition capture that intuition? And for this, we can't just appeal to intuition. We have to go back to first principles. What is the structure we looked at? Does a rule of products emerge from that structure? If it does, then we can conclude independence. If it does not, then sadly we will not be able to. So let's go back and write down what we need. We want to ask something about the probability of the intersection of these two new events, A and B complement. And I've given you an identity. Do you recognize where it comes from? Well, naturally, we are using additivity. Think of an event A. The events B and B complement partition space, and therefore the chance of A can be decomposed into the chance of A, which is a part of B, and the chance of that portion of A, which is a part of B complement. This is additivity. Move one of the probabilities to the right, and you've got the identity in front of you. This is very nice, because on the right, we have a term which represents a probability of a conjunction, of an intersection. But if we know events A and B, we know that that can be decomposed as a product. This is what independence gives us. Oh, this is lovely. The moment that happens, I've got on the right various terms, and naturally, I factor out common factors. In this case, the probability of A. And then in round brackets on the right, I get 1 minus the probability of B. Aha, that's familiar. I recognize that via additivity again as the probability of B complement. Remember, B and B complement together split up the whole space. Normalization tells you the entire space has got probability 1, and therefore we got by additivity an identity. On the left, the probability of the conjunction of A and B complement. On the right, the product of the corresponding probabilities. By the definition of independence, we conclude that A and B complement are indeed independent. But then what about other combinations? What about A complement and B complement? What about A complement and B? Let's pause before we do any more analysis. Okay, what has our analysis told us? If you start with two events, A and B, and they're independent, if you complement any one of them, then the two are again independent. So if you complement B, then A and B complement are independent. Of course, we could have done exactly the same analysis if we complemented A, which means A complement and B are independent. But if A and B complement are independent, then if you complement one of them, you again get independence. So if you complement A, then A complement and B complement are independent. What we just discovered is that one identity, that one rule of products on your upper left, right, that implies all the other rules of products for various complement conjunctions. And therefore, any one of these independence relations implies the truth of all the others. Oh, this is very nice. Elementary, I know, but still very nice. This gives us confidence that the mathematical structure is indeed capturing the physical kinds of reality that are vaguely referred to as independent. Here's the mathematical structure. Now we want to build upon this and see what it says in applications where independence is not nearly quite so clear. That is our next step.